look at fields, again, there's electric and there's magnetic fields. It's used to explain why, when things aren't in contact with each other, when I take one charge thing, so in the torsion balance, you had a charge, and when it came close to another pith ball that had an opposite or same charge, and it would repel, but they actually never touched. Forces are what help explain that dynamic. So fields are action at a distance. It's kind of a weird way to say it, but that's what it works best. When we have, let's say we look at Earth, over here we have, and then we have North America over here. Okay, electric fields, when we draw lines like this, they work inwards. Okay, they have an effect going towards the center of that object. So fields are vectors. They have a direction. And the biggest one, a vector field would be the gravitational field, right? The field of gravity, or the force of gravity, always works towards the center of mass of the object. In this particular case, it's Earth. Okay, if we were on the moon, we would look at it and it would be towards the center of the moon. And so we draw lines inwards. Just as every mass creates its own gravitational field, every charge creates its own electric field. So if we look at we can look at 4 different situations here. If I have a positively charged ion or a positively charged object, the fields radiate outwards. If I have a negatively charged object, the electric fields radiate inwards. Okay, and that makes sense that the field lines go this way. If I wanted to show you that there was a high level of an electric field, if I had positive, the way we show that diagrammatically is we increase the intensity of lines, the quantity of lines around it. Oh, I drew it the wrong way. These go out, sorry. No, they go out. This is why Miss Pyre doesn't write in pen. Positive fields go out. Negative fields go inwards. And again, if I wanted to show the increased intensity, I would show you more lines. Okay, so this is a weaker electric field, and this is a stronger electric field. So it's inward on negative, and it's outward on positive. Okay? Regardless to what silly mistake I make. And then here there's a sentence that says, the interaction of electric field lines, can help explain why similar charges repel. and opposite charges attract. Because if I have a positive and a positive and it's radiating outwards, it's not going to go from, it's not going to do this. It's not going to go like this and like this. They're going to bend away from each other. They're going to radiate like this. They're going to repel away from each other. Positive or negative. Negative will do the same thing. And it will come in like this. Okay. This area here in the middle, this area here in the middle where it's repelling and attracting, there is no electric field here. If you were to find a way to measure this, there would be no value. Now, if I have opposite charges, we know that positive charges radiate outwards and negative charges radiate inwards. So you can see this flow. Okay. When we look at the formula, when we look at F is equal to K1 Q2 over R squared, the strength of the field, electric field, depends on the distance from the charge. So there is a relationship, and we don't use that's force. We use this symbol E, electric field strength, is equal to K Q over R squared. Okay, and again we use absolute values. We don't care if there's a positive charge or a negative charge. We just need the value from the charge. Okay, so E represents electric field strength. If you look on your data table, it's in the bottom left-hand side of the table. E is equal to KQ over R squared. Do you see it there, Cadence? It's at bottom, or is it in the middle? In the middle? Okay. K is still 8.99 times 10 to the 9. It's still a constant. Q is the charge. This is key because this helps us when we're reading questions. The object producing the electric field. So when we're decoding questions, we want to look for those kinds of words. And R is the distance from the charge producing the electric field. Because we're going to learn a lot of formulas in this unit, and we need to be able to know which one we're using at which time. So from the equation, we see electric field strength and distance have a proportional relationship. So if I did a graph, and I did E versus R, what kind of graph would I see? That. Okay, when we're looking at just R. How would I straighten it out? I would do 1 divided by R squared. That's how I would straighten it out. So electric field equation looks very similar to gravitational field strength. Gravitational field strength in relationship to R has the same kind of graph. If I wanted to straighten it out, I would have to do 1 over R squared to straighten it out. Okay? So the electric field strength can be calculated based on force of another charged object. So here we see the relationship between electric field strength being equal to the electric force divided by the charge. Okay? So now the difference is this is the object in the electric field, not producing it. It's already inside the electric field. Okay? So those are two key points that we know when it's producing it versus when it's inside of it. If we look at the first example, if the distance from a point charge is tripled and the charge of the point charge is also tripled, by what factor does the electric field strength change? So if I have on my original, I love that my mouse, my computer has a mind of its own. This formula, E is equal to KQ over R squared. Okay. I have original value of E based on some value of K, Q, and R. Okay. When I modify it, I have my new value that I'm looking for. My K is a constant. My Q, it tripled, so it's 3 times my original value. And my R is 3 times my original value. So when I go E is equal to KQ over R squared, I'm going to have 3 over 3 squared times the original value. And so I get 3/9 of my original field strength, or 1/3. Okay? If I look at the next one, determine the electric field strength 0.7 meters south of a negative 8.5 microcoulomb charged object. So when I look at that picture, my electric field strength is pointing inwards, and my point is 0.70 meters, and the charge is negative 8.50 microcoulombs. The way to find electric field strength, KQ over R squared. What are some things we need to pay attention to? Microcoulombs has to be changed into coulombs, so negative 8.50 times 10 to the negative 6, that's what micro is, coulombs. So 8.99 times 10 to the 9 multiplied by 8.50 times 10 to the negative 6 divided by 0.7 squared. And I would get what for a value? We don't use the charge. We use absolute values. So if this point is south of this charged object, which way is that electric field strength going? It's going to flow in towards the charged object. And we don't put the charge up front, this, if it's positive or negative. Okay, because we know that in our world, south is a negative value, but the charge, the point creating the source is already south of. So the electric field strength is going to flow up towards the negatively charged object, which is north. A plus 5 microcoulomb charged object is placed in an electric field of 2.2 times 10 to the 4 newtons coulombs to the east. Determine the electric force acting on the charge. So a positively charged object is placed in an electric field to the east. So it's going to flow this way. If it's going to flow, chances are that it's going to be a negative value here, a negative ion. Otherwise, it would repel. Okay? The charge is placed in an electric field. So we're not looking for E, we're looking for the force electric. The way that we're going to do that, though, is by using this, because it's in the electric field. And this is what we're looking for. So force electric is equal to EQ. What's something that we have to pay attention to? Microcoulombs. Okay? So 2.20 times 10 to the 4 newtons per coulomb multiplied by 5.00 times 10 to the negative 6 coulombs. So force electric gives us what value? What? 1.1? You guys get the same answer? What did you get, Cadence? 0.11. You're out by a factor of 10, Daniel. Okay. So 0.11 newtons force has direction. So what direction would we say this is? East. Okay, what is the electric field strength midway between charged objects of negative 3.5 microcoulombs and 3 microcoulombs that are placed 0.44 meters apart? So here's the charge. And it's asking us a midway point. What is the electric field strength midway between charged objects? So which of these two formulas are we going to be looking at? Pardon me? KQ over R squared, because it's the point that's affecting a field strength. So we're going to look at this one first. And then we're going to look at this one. And these objects here are from here to here is 0.440 meters. But it's saying midway, so our R is actually going to be 0.22 meters. Okay? Something that we need to look at then is what is the lines of electric field strength on something that is negatively charged? Inward or outward? Inward. Okay? What about something that's positive? Oh, you were so close. Outward. Okay? So when I look at this, the field strength that point P is affecting on this negatively charged object is going to the left, which is positive or a negative sign? Negative. Okay? On a positive charge, the field strength is flowing which way? Away from or towards point P? It's flowing towards point P. So it is also negative. So then when I look at electric field strength, it's going to be E1 plus E2. So negative 6.50 times 10 to the 5 plus negative 5.57 times 10 to the 5. And E net gives me which value? Newtons per coulomb. And then which way is it flowing? Your value was negative, so it's to the east, left. Same thing. Left is easier. Okay? Questions, comments, or concerns?